Okay, great. So it's a pleasure to introduce the speaker today for this quick special seminar. So Manideep Manindlapally is visiting from CWI. He's a PhD student there, working on questions related to quantum computing, quantum query complexity, sort of related topics. It's great to have him here visiting for the rest of the week. So I think there's some room in his schedule if you're interested in meeting with him. Maybe people can just speak to you directly. We have a schedule that's been going around, but I think you can just speak directly with him. So thanks very much for coming to visit, and please take it away.
Thank you. Good afternoon, everybody. Thanks for the introduction. So I am a PhD student at CWI in Amsterdam, and I'll be talking about a topic I've been working on for the last few months. It's conditional low bounds for algorithms with pre-processed deadweights. This is a work with two of my supervisors, Stacy Jeffrey, Florian Spellman, and Subhasri Control. So I will try to focus the talk on, this is ongoing research, so I will try to focus the talk mostly on some previous literature, and which is mostly classical conditional lower bounds. Towards the end, I will give some ideas how we can quantize these reductions. And throughout the talk, feel free to interrupt and make comments or ask questions. That would be very nice. The outline of the talk will be like this. I will introduce fine-grained complexity via a threesome problem. Then I will move to talk about space-time trade-offs through the context of data structure problems. One such example is the threesome indexing problem. And then I will show a reduction, give a sketch of a reduction between two problems, two conjectures, the threesome indexing conjecture and the SetDisjointness conjecture. Yeah, so you might know the complexity class P. P is the class of problems, class of all the problems that can be solved in time that is polynomial in the input size. Some people say this characterization is not super useful because it includes problems that take square root n time to solve, and also problems that require n power 100. Right. So fine-grained complexity is just the study of a more fine-grained analysis of the running time of these algorithms, where you are interested more in the exponent of the polynomial. And some problems have been studied extensively, like this matrix multiplication, graph reachability, set intersection, string problems, and the threesome problem, which I will focus on today. And then in a particular area of fine-grained complexity is conditional lower bounds, where people study reductions between different problems, which helps them to prove results of the form. If problem A is so and so hard, then a reduction from problem B to problem A would mean that problem B would also be hard, conditioned on A being hard. Let's take the threesome problem. In the threesome problem, we have an input of 3 arrays of all integers for now, let's say. And you're supposed to output if there are 3 numbers, x in the first array, y in the second array, and z in the third array, such that x plus y plus z equals 0. Now this can be solved classically in square log n time using a plain brute force search, which can be improved to n square time using some pointer based improvements. And then there were works recently, which there were works very long ago, so from 2005, which improved the performance to n square by log n, which could be further improved in some special cases to n square by 2 power square root log n and n square by log n power c. Right, but they couldn't get the exponent down to under 2. Right, and so naturally they conjectured you can't get it down to under 2, and that became the famous threesome conjecture. It's that there is no classical algorithm that takes subquadratic time and can solve the three-sum problem. Now I put it that way, but this three-sum conjecture is widely believed to be true, and it is used to prove conditional lower bounds for a bunch of other problems: geometric problems, graph problems, data structure problems, string problems, and it occupies the same standard along with a few other assumptions. Set and APSP, set being the strong exponential time hypothesis, and APSP being the all pair shortest paths conjecture. And these conjectures can be used to prove conditional lower bounds for a bunch of other problems. Now all this is the so far it's been classical, and when we go quantum, this three-sum conjecture can directly be refuted by using Grover speedups. And so two of my collaborators, Shubha and Florian, proposed the quantum three-sum conjecture, which says there is no algorithm that can solve the three-sum problem in sublinear time. And they use this to prove conditional lower bounds for some computational geometry and graph problems. And this works by, in a similar way as in the classical case, you make quantum reductions now to three-sum instances from these problems. Even though the techniques are mostly inspired by the classical reductions, it would require some speeding up, some non-trivial speedups, just because you are trying to prove a stronger lower bound in the quantum case. So that's all the time complexity. But oftentimes, what is also important, especially in quantum, and what makes spectacular news headlines is the number of qubits, which is the space of computation. And so conditional lower bounds have also been studied in this context, space-time. And those are called the space-time trade-offs. Now in this talk, I will look at the trade-offs in space between space and time in context of certain pre-processed algorithms for certain data structure problems. To understand data structure problems, think of a cheat sheet exam. I TA a course at University of Amsterdam, the quantum information theory course, in which there are exams where the students are allowed to carry a cheat sheet. A cheat sheet is usually an A4 size sheet where the students can fill in formulas and definitions, whatever they think is useful, is helpful for them to quickly answer the questions in the exam. Now, this activity can be viewed as happening in two phases. In the pre-processing phase, the student processes all the lecture notes and textbooks and try to condense them into a cheat sheet, into an A4 size sheet. They're bounded by the size of the sheet, which is, let's say, an A4 size. They're not bounded in the sense of time. They could spend just the previous night thinking about this, or they could spend the entire semester writing down the cheat sheet. And then in the query phase, which is the exam, is when they get asked questions, and they use the cheat sheet to answer the questions as fast as they can. So the time is of the essence. And we are interested in trade-offs between the space and time resources. Now I'll go on to explain the three-sum indexing problem, which is a data structure variant of the three-sum problem. This was the three-sum problem I quickly mentioned earlier. There are three arrays, A1, A2, A3, integer arrays, and you have to find if there exists X, Y, and Z that sum up to 0 from these. Now the three-sum indexing has, in the first phase, the pre-processing phase, you get two arrays as input. You can pre-process them to output a string, an advised string, alpha. And then in the query phase, you get asked an input, let's say Z, coming from the same universe. And then you have to output if there are two numbers, integers, x in the first array, y in the second array, such that x plus y equals z. In the query phase, you can use the advice alpha. You can, after staring at this problem for a while, you can come up with an algorithm that uses n square sized advice and can solve a query in constant time, right? You can exhaustively store for every element in the array the sum x plus y. And then you can sort it, and then you can perform a binary search in the query phase, whether z belongs to any of the elements in the list or not. Similarly, you can come up with an algorithm that uses advice of size n and answers the queries and n time. So this would be the plain algorithm with which you would try to attempt when you are not allowed a data structure, but you still need to store the input arrays, which would take n length. So you would take n length. Yeah.
How do you get like n instead of n squared? If you just sort of
Yeah. So in the first, yeah, thanks for asking. So in the first case, I do not really explain. So we are not storing A1 and A2. We are storing kind of A1. We are storing A1 cross A2 kind of. So for every pair of elements belonging to A1 and A2, we are storing their sum. And then once we have like an n square sized list of all the sums, we sort them out.
And what do you do in the second bullet point where you only have n space?
Yeah. So in the second bullet point is what you were saying. So we store the arrays as the inputs that we got. We store the arrays just as they are, and then we can sort them out in the pre-processing step. So we store the sorted arrays, and then we search over the sorted array. Let's say one. So let's say on A1, search exhaustively for every element in A1. We do a binary search for z minus that element in A2. So that would take n times log n time. So in this paper by Goldstein, Kupelovitz, Lowenstein, and Horat, they've proposed a three-sum indexing conjecture. The strong variant of which is that there is no algorithm with size that with an advice of size that is subquadratic and takes time that is sublinear, right? Because what happened here was there was an n square sized advice, which when got down to a linear size, increase the time from constant to linear. This is a classical conjecture. You can applying in the second algorithm by applying a quantum speed up in the search, you could get an algorithm that would take square root n time. So the quantum three-sum indexing conjecture would be this. There is no algorithm. Would be that there is no algorithm that takes subquadratic that takes a subquadratic sized advice and solves the three-sum indexing problem in sub square root time. Yes.
How do these conjectures compare? Like, if you break one, you break other, or like, can you just break one without the other?
Yeah, so far there is no comparison. So we would like to make a comparison between the quantum conjectures and the classical ones. Uh, but now what I will talk about is a similar conjecture for a different problem, classically and then quantum, and how these two relate among each other. Another data structure problem I'd like to talk about is the set disjointness problem. In the set disjointness problem, in the preprocessing phase, you get m different sets, such that the total number of elements in all of these sets is upper bounded by this at a capital N. You can preprocess them, all the sets, and store an advice string alpha. In the query phase, you get input two indices I and j, and you have to output if the corresponding sets Si and Sj are disjoint or not. Now, similarly, again, you can actually store, like exhaustively store, for every pair of sets, whether they are disjoint or not, in the preprocessing phase itself, right? And then in the query phase, you can just look up the table whether the intersection is a null set or not. And on the other hand, if you were not doing that, you store all these elements of the set, then you can come up with an algorithm that's that given two sets performs like a search. So in the same paper, they make a conjecture for the set disjointness problem. It's that for all algorithms that take time t, they need an advice of size at least n squared by t squared to solve the set disjointness problem. And the quantum set disjointness conjecture would be that for all algorithms that take time, would require advice of size n squared by t power 4. In fact, in this paper, they do this reduction between a bunch of different problems. You see, what I was talking about was three-sum indexing and set disjointness problems, but they do it for a bunch of other problems. And these arrows correspond to the reduction that the arrowhead points to the conjecture that is implied, and the arrow tail corresponds to the conjecture that is conditional. So, for example, this arrow means that the directed reachability conjecture means some conditional bound on some dynamic problems. Now I will focus on for the rest of this talk. I will try to give sketch a reduction between these two conjectures, the three-sum indexing conjecture and the set disjointness conjecture I just talked about. The idea involves some techniques which were inspired by similar reduction between the three-sum problem and the set disjointness problem in not the preprocess setting, but in the regular setting, but involves some modifications to fit the space picture. So to prove this conjecture, you would reduce a three-sum indexing instance, which is this A1, A2, and then Z, and then we reduce it to an instance of two instances of set disjointness problem. Now, note that the reduction is happening in two phases because we have a pre-processing phase and a query phase. So the reduction would also involve two steps. And this is the conjecture we want to prove. Sure. And should I?
Oh, sorry. Yeah. Yeah, these are the markers that I checked, so we start with this.
Okay. We are starting with an input instance. A1 and A2, right? And this is the reduction in the pre-processing phase. What we do is we pick a hash function that is linear and balanced. That goes from the universe U to some indices up to R, right? Where R is now a parameter. And then you would form a bin of inputs according to the hash function outputs. Right? The bins would be like this. So Pi is a bin which contains all the inputs such that h of x equals set of bins from A to N. Now I said this hash function is balanced and linear. So what balanced means is that the bins are almost balanced. There are very few bins which would have more than a certain number of inputs. The expected number of x's is that x belongs to a bucket that is unbalanced. Size of vi is greater than this number. Is small. What this means is because this is a linear function as well. Let's say there is a yes instance. Let's say later, when in the query phase, when you get asked Z, there is x belongs to A1 and y from A2 such that x plus y equals Z. This means h1 of x plus h1 of y equals h1 of z. This means if h1 of x was equal to I, So what this means is there exists an intersection between the bucket Bi, which is X. I- what this means is there is an intersection between the set Bi and set Now we have to check this. Okay, but this intersection is not an easy thing to transfer to the set disjointness case because this intersection involves Z as a difference you do to one of the sets. Like you don't know what Z is in the pre-processing phase, so you don't know which sets to give to your set disjointness solver. So what you would do is pick another hash function that is pairwise independent. And Q is another parameter. And you construct similarly bins. So this is a construction which was inspired by the result which showed reduction from threesome to disjointness. There is an intersection. What this would translate to is that it's not straightforward, but once you write down, then you
that a my CI? Right side.
follow. So now we've reduced this input instance to sequence of sets Bij, Cij, which we would use as instances of the set disjointness problem. So we would use this to pass it on to the algorithm which could solve set disjointness problem, and we would get an advice of, let's say, an advice alpha. And then in the query phase, get input Z. What you would try to do is search for different I such that these both sets are disjoint, right? So search
What is the,
set R, because I comes from the set R, which is smaller than N, such that this will absolutely small fractions. So yeah, so let me try to explain why this condition is. Understand again. Again. So in case of an yes instance, there is an input Z such that X plus Y equals Z. Right? That means Y equals Z minus X. Right? And the hash output of Y would be because of the linearity condition, this would be and h1 of x was equal to r. Right? And this means y belongs to the bucket C this implies because y belongs to this bucket, x is nothing but equal to z minus y. So x belongs to the bucket. That added was the element. Yeah. Sorry, okay. Does anybody want to ask a question here? Yeah, sorry, it's a bit convoluted to process, but I will also give you the reduction on the other side, which is a little bit simpler. I'm trying to prove the other side of the conjecture, which the other side of the relation, which is that set disjointness conjecture implies threesome indexing conjecture, which means I start with an instance of set disjointness problem, which are some sets S1, S2, Sm, such that the total number of elements in all of these sets is less than n. I'm trying to generate an instance of the threesome problem, which would be two arrays, right? So maintain arrays A1 and A2. And for every element in every set, construct two integers, xa and xb. These are integers whose bit string representations would be like this. The bit string representation will have three segments which are padded by zeros in between. The first segment of xa would be the value x of which is the element. The second segment would be I, which is the index of the set, and the third segment would be just 0. And xb, the second integer, would be m minus x in the first segment, where m is, let's say, the maximum of all of the x's. The second segment would be zeros, and the third segment would be pi. And then append xa to the array A1. Append x to xa, x. And then in the query phase, you get asked, let's say, to find out if I and j. That means if you want to find out if Si and Sj are disjoint or not. To do that, you query Z, which is prepared for life. Yes.
Why is it? I guess I would have expected like minus I and minus j.
Minus I in the pre-processing phase?
In one of, yeah, I guess maybe my question is like, yeah, how does this work?
Yeah, let's see how this works. So in case it was yes, that means their word Si and Sj are actually intersecting. Okay, that would be no instance. Si intersection Sj is not equal to 5. That means, let's say x was the element of the intersection. Then XA, in our construction, you would come across XA, which is when X belongs to Si, when you were pre-processing X belongs to Si, you would have this element. And there is also another element when you were pre-processing the set Sj. The second element would be now when you solve for the threesome problem with both of these numbers, when you add XA and XB, you get J in the first segment, I in the second segment, and M in the third segment, which is exactly what we are looking for. Which is exactly we say what we are looking for. So the threesome algorithm should return a yes or no. The threesome algorithm would return a yes, and we would say no. There is no. These sets are actually not disjoint. Now, actually, this characterization is an if and only if characterization, so it also works for the yes issues. Now, this reduction is actually can be trivially sped up even in quantum, because in this reduction we are reducing one instance of the set disjointness to just a single instance of the threesome problem, and there's really not much happening in this reduction. The query phase reduction is just taking constant time, so that you can't hope to get any speed up here. But the earlier reduction I mentioned would involves a search, which you can speed up is quantum searching. Yeah, that's about it. Thank you.
So you presented this directed graph of reductions between various conjectures earlier on. And we've only looked at a few of them that also have quantum analogs.
Yeah.
Are there quantum analogs of some of the other items? Because there were some interesting things there, like binary matrix multiplication and stuff. Or at least the quantum reductions kind of break down somewhat.
Yeah, we are actually trying to look, so most of the reductions are actually kind of straightforward. In the sense, is like this reduction basically. They're interesting to look at, but they hold trivially even for the quantum case. The threesome indexing to the set disjointness was one conjecture, which involved like a Brouwer speed up. Yeah. I haven't looked at exhaustively the entire graph. I don't have it here. But most of them are the K reachability, directed reachability, and Boolean matrix multiplication reductions have no non-trivial speedups.
Are there any examples sort of known where there are kind of surprising kind of improvements in the space-time trade-off quantumly compared to what happens classically? Like, I guess in all the examples that you talked about, it's kind of like, there's some improvement that comes quantumly from some quadratic speedup somewhere, but it's, there's some kind of natural quantum analog what happens in the classical case, but are there, if you were to sort of go looking for a case where there's like the kind of most interesting thing that happens quantumly, like the most surprising trade-off, I don't know, is there an example that you can point to, or is there kind of nothing known like that?
Yeah, nothing known. We are looking for that actually.
Yeah.
But we are also studying slide future.
Do you want me to put it back up?
No, it's fine. It's just one slide I can bring it out. So it's just we are also looking at trade-offs between not just preprocessing space and preprocessing time. We're looking at trade-offs also between preprocessing time and the query time, and there we are observing. We are looking at this problem where reducing convolution threesome to, which is just a variant of the threesome problem, the convolution threesome problem to a data structure problem, which is convolution reporting, which is like if you have two vectors and you have to report like the indices where the convolution of these vectors would be non-zero, something of that sort. And that would involve some not trivial structures. It involves some tree evaluation structures, and then we are hoping to find some speedups in there.
Yeah, I don't know if this is important at all, but I was wondering for the SetDisjointness conjecture, that conjecture is formulated as a relation between S and T, right? It's like you're conjecturing like S has to be at least like n squared over T to some power.
Yeah.
Whereas in the three-sum index conjecture, it's there's not an explicit relation there. Is that at all important?
Yeah. So that's right. But there's difference in the way I stated the conjectures. The way I stated the three-sum indexing conjecture, even though I say it's a trade-off, it's actually saying there is no trade-off. That if you go sub-quadratic space, then the time would be at least linear. Anything sub-quadratic is linear. Whereas the way they conjectured in paper is that there's like a relation for space. So right. This is because for the SetDisjointness problem, you can think of like at least the quantum analog I can think of is this trade-off is more observed is that you can think of not storing all the subsets, but kind of a subset of all the subsets and performing like a Johnson graph on all of these sets with these smaller subsets. So you have a gradation in reduction in the space, but you would end up spending more time solving. But a similar structure is not expected to exist in threesome indexing, which is why they conjectured. But of course, it's not proven. Does that answer? Yes. Thanks for the nice picture.
Other questions? Okay, well, if not, let's thank you again.